All right. So welcome to your first lecture on metabolism. Good morning. We are going to start off with glycolysis and gluconeogenesis. This is going to take us 2 sessions. So we'll start it today. We'll finish it tomorrow. My one piece of advice for going into metabolic pathways is that oftentimes some things don't quite make a lot of sense in the beginning because you don't know the full story yet. So you kind of have to be a bit patient for a few slides later, or maybe for the next lecture, so everything comes together. So if something is a bit unclear in the beginning, something seems confusing, be a bit patient and then it will fit together. There are 2 ways to teach metabolic pathways. The one way is to essentially tell people, here's the overview, here's what happens in an overview way in metabolic pathways, and then you go and look at each pathway. Or you can teach the different metabolic pathways and then put it all together at the end. In other words, you can give a person an image of the forest and then go through the individual trees, or start with individual trees and then look at the forest all together. I start with the trees. I think it's simpler this way to understand bits and pieces and then put it all together. So we're going to start off with glycolysis and gluconeogenesis. Okay. All right, so I've made a little diagram here to kind of starting to orient ourselves. Here's glucose, very, very important molecule, very central, kind of like a hub. And then what do we use glucose for? I'm sure you know that we use it for extracellular matrix proteins, right? There's proteins that have carbohydrates attached onto them. Oftentimes, these carbohydrates are glucose or glucose derivatives. So we use it for that. Another thing we can do with glucose is we can store it as glycogen for a rainy day. In other words, when we are in need of glucose, we can go back to glycogen and take glucose from there. And I'm happy to inform you that we will be spending 2 whole sessions on glycogen. So we'll leave that to that. And then we have the pentose phosphate pathway, which is another pathway that utilizes glucose. This pathway will be our first lecture in biochemistry 2. But this pathway essentially uses glucose to produce ribose 5-phosphate, which is necessary for nucleotide biosynthesis. And then we have, of course, the grand entrance here of aerobic respiration and anaerobic respiration, because this is what we're going to focus on. So we're going to take glucose. Today, we're going to convert it to pyruvate. We're going to convert pyruvate back to glucose, and then we'll talk about the rest in upcoming lectures. So I call this the complete oxidation of glucose, a biochemical trilogy. So just like every trilogy, it has 3 episodes. Episode 1, lecture today and tomorrow, is going to be on converting glucose to pyruvate. And of course, we also have to discuss pyruvate to glucose conversion as well. Episode 2 is everybody's favorite cycle, the Krebs cycle. Okay. You know, people tell me, what do you do for a living? I teach biochemistry. Ooh, the Krebs cycle. That's what I'm known for, I guess. So episode 2 is the Krebs cycle. That was going to take us 1 session. And episode 3 is oxidative phosphorylation, which will take us another session. So we'll take 4 sessions altogether to go through these 3 episodes. Okay, the first one is rather big, so we need 2 sessions. So that's the ultimate goal, for us to go through this pathway. This pathway is perhaps the most central to metabolic pathways. After this, all the pathways will feed into or out of these guys. So if you have a good, solid understanding of this, it kind of helps you understand the upcoming lectures as well. All right, so let's talk about glycolysis. The first thing I want to say is, whenever you have to deal with a metabolic pathway, I want you to put a note for yourself to make sure you know, where does this pathway happen. So for glycolysis happens in the cytoplasm of all cells. So that's a piece of information that you need to know. It's going to come in handy, trust me, if you know in what cells and in what part of those cells do these pathways take place. And for those of you who are planning to take the USMLE, this is a concept that they really like as well. They want you to know where each pathway takes place. And you will see it will be useful for your understanding, okay? So by definition, glycolysis is the conversion of glucose into 2 molecules of pyruvate. Glucose has 6 carbons, pyruvate has 3 carbons. That's why you get 2 molecules of pyruvate for every molecule of glucose, okay? I put here the overall reaction of glycolysis. We'll go through it. And I put here that the delta G of this pathway is minus 96 kilojoules per mole. You don't have to memorize that. I just put that number there to show you that it's a negative number. When you want a pathway to actually take place, the overall delta G has to be favorable, right? You want a pathway to be energetically favorable. So you want this energy to be negative. So it is negative. That's great. This means this pathway can take place. Okay, so I'm going to go through the steps of glycolysis. You do not have to memorize any structures, and I will explicitly tell you what things you need to memorize, okay? Step 1, glucose gets converted to glucose 6-phosphate via this enzyme called hexokinase. If you look at the arrow here of the reaction, it's a unidirectional arrow. In other words, hexokinase can convert glucose to glucose 6-phosphate. The reverse is not possible with this enzyme, okay? I'm sure you guys know that glucose, we'll discuss it at a later time in more detail, but I'm sure you know glucose can get in and out of the cells. In different types of cells, we have glucose transporters. Now, once you convert glucose to glucose 6-phosphate, glucose 6-phosphate gets trapped in the cell. There's no way for it to get out, okay? So that's one of the advantages of this reaction being going only in one direction, is that when you get glucose 6-phosphate, people say this makes glucose get trapped in the cell, so it can never go out again, okay? So this is a reaction I would like you to know, and I'll tell you a bit the rationale behind this. But you need to know that the first step of glycolysis is catalyzed by an enzyme called hexokinase. It converts glucose to glucose 6-phosphate. What happens then? Glucose 6-phosphate gets converted to fructose 6-phosphate. Perhaps you remember from last year when I came to your year 1 at the end, when I was saying about glucose and fructose, that they're both C6H12O6, but they look different. They have very different 3D structures. So what happens is here, there's an isomerase, an enzyme that converts the one isomer, glucose 6-phosphate, to fructose 6-phosphate. It's a very difficult reaction to take place. You actually have to break the glucose ring and reform it in a way to get fructose 6-phosphate. But you see it's an equilibrium sign here now, which means this enzyme, phosphohexose isomerase, can catalyze this reaction both ways. You do not need to memorize this enzyme. Then what happens? Fructose 6-phosphate gets another phosphate added onto it to become fructose 1,6-bisphosphate. I think in my experience, everybody has heard of PFK before, right? Phosphofructokinase. Great idea for a password for your email or anything. Nobody will crack it. People, I'm telling the exams office to put this password, but they're like, how are we going to open the exams then? All right, so fructose 6-phosphate has to become fructose 1,6-bisphosphate. What we are essentially trying to do here is we're trying to get to pyruvate. We're trying to get this glucose molecule split into 2. And glucose is very stable, so what we're doing is we're actually trying to do our best to destabilize it. That's what phosphates do. So we have now fructose 1,6-bisphosphate. This is an enzyme you need to remember. Anybody knows why I'm asking you to remember it, perhaps? From previous knowledge? It's the master regulator of glycolysis, and we'll discuss this in a bit. So this is going to be a very important enzyme. you need to remember that phosphofructokinase catalyzes the conversion of F6P fructose 6-phosphate to fructose 1,6-BP fructose 1,6-bisphosphate. Okay? And then what's going to happen? This fructose 1,6-phosphate is going to split into two. We've destabilized it enough so that there's an enzyme called aldolase that can come and split the molecule into two. What are the two molecules you get? Dihydroxyacetone phosphate, which people abbreviate as DHAP, and glyceraldehyde 3-phosphate, which people abbreviate like a clothing brand, Gap. Okay, so you split fructose 1,6-bisphosphate, you get DHAP and Gap. So you see here it says Gap proceeds to step 6, but DHAP proceeds to step 5. Now, mind you, we're at step 4. And so Gap can go all the way to 6, step 6, but DHAP goes to step 5. What's step 5? DHAP gets converted to Gap. So you see what happened there? Fructose 1,6-bisphosphate got split into two, DHAP and Gap. And then DHAP becomes Gap as well. So essentially you get two molecules of glyceraldehyde 3-phosphate. And then the glyceraldehyde 3-phosphates continue on with glycolysis. Okay? So here we go. Dihydroxyacetone phosphate becomes glyceraldehyde 3-phosphate through this enzyme called triose phosphate isomerase. If this enzyme did not exist, you would only get one molecule of pyruvate for one molecule of glucose. You would have lost half the efficiency of glycolysis. So not only it's great that we have this enzyme, but it's a catalytically perfect enzyme. In other words, we couldn't envision a more efficient enzyme to do this reaction. So once now you have two molecules of glyceraldehyde 3-phosphate, they get converted to 1,3-bisphosphoglycerate. Okay, so essentially another phosphate gets added onto it. What happens next? 1,3-bisphosphoglycerate becomes 3-phosphoglycerate. The ATP gets donated, the phosphate group of 1,3-bisphosphoglycerate gets donated to an ADP to become an ATP. And then the 3-phosphoglycerate becomes 2-phosphoglycerate. Basically, the position of the phosphate group changes. And then 2-phosphoglycerate becomes phosphoenolpyruvate. And phosphoenolpyruvate, finally, we're getting there, becomes pyruvate. So these are the 10 reactions of glycolysis. And I just went through them very fast because you don't have to memorize anything other than the specific things I mentioned, and I will recap again. If you notice, this last step, phosphoenolpyruvate to pyruvate, is also a unidirectional arrow. So if you go back actually and you look at all the reactions of glycolysis and you look at their arrows, you will realize that all the reactions are equilibrium reactions. In other words, the reaction can happen both in the forward and in the reverse direction, except the 3 reactions that you see here in red. These are the ones you need to know. You need to know the enzyme name, the substrate, and the product of these 3 steps. Don't worry about memorizing structures. Just remember the names of the enzymes: hexokinase, phosphofructokinase, and pyruvate kinase. So 3 enzymes you need to remember, and you need to remember what are their substrates and what are their products. Why? I will explain in a bit why I want you to focus on these 3. Is that okay? Is it clear what you need to remember? No worries about memorizing other pathways. Okay. And I put a note here. If you look at the reactions, some are very energetically costly, some give off energy, but the bottom line is that the overall pathway has a negative delta G, which makes it overall favorable. Okay. So I have a question for you. If glycolysis is by definition the conversion of glucose to pyruvate, gluconeogenesis is the conversion of pyruvate to glucose, so the reverse. How do you think these two pathways will be different? If going from glucose to pyruvate looks like this, how do you envision going from pyruvate to glucose looking like? You start from the bottom up. Do you think any steps will be the same? Yes? Exactly. Do you want to add, or you wanted to say? So the ones that are reversible are actually going to be the same thing, right? If you start from the bottom up, all the reactions that are reversible can still happen. So what's the difference between glycolysis and gluconeogenesis? Essentially, those 3 red steps. That's why I'm asking you to memorize those 3 steps only. And you'll see they'll come in handy. Okay. Any questions? So here's a summary of glycolysis. I just want to emphasize that you start with 1 molecule of glucose. So up until the point where you have fructose 1,6-bisphosphate, the first 4 steps, they take place once for every molecule of glucose. But after this, everything happens twice for every molecule of glucose. Because you see in the bottom, we have glyceraldehyde 3-phosphate, which continues with the pathway, but we have dihydroxyacetone phosphate, DHAP, which gets converted to glyceraldehyde 3-phosphate to continue with the pathway. So everything after on the next slide happens twice for every molecule of glucose. That's why you see a 2 in parentheses in front of every molecule here. If you now go back and you check the number of ATPs, you will see that you utilize 1 ATP here, another ATP here. So we've utilized 2 ATPs. And over here, we have produced 4 ATPs. We've used 2 ATPs, we've made 4. So there's a net increase, a net production of 2 ATPs. And there is a net production of 2 molecules of NADH. So that's how you get the overall reaction. It's glucose giving you pyruvate. In the process, you produce 2 molecules of ATP and 2 molecules of NADH. There was no oxygen used in glycolysis, so glycolysis is actually an anaerobic pathway. Okay, so there's no oxygen as part of glycolysis. In high school, didn't we learn that, cellular respiration is glucose plus oxygen to give you energy? What a lie. It doesn't happen in that sequence. That's just an overall generalization. You don't start with using oxygen. Actually, you will see oxygen is used at the very last step. Yes. For these slides, all steps 1, 3, and 10 as well? Exactly, they're the same as here. 1, 3, and 10. And all you need to know, the name of the enzyme, hexokinase, phosphofructokinase, pyruvate kinase, the reactant, and the product. And you will see as I go along why they will become important. Any other questions? Okay, do not waste your time memorizing other steps or memorizing structures. Sure, you can go over the steps if you want to see if you understand what's happening, but really no need to go into details. Okay, so I like bringing in diseases as part of these lectures. There's a big class of disorders called the inborn errors of metabolism or hereditary metabolic disorders. Those terms are used interchangeably. And here's our first one, pyruvate kinase deficiency. Pyruvate kinase is the enzyme that catalyzes step 10 of glycolysis. So imagine if you have a deficiency in that enzyme. Well, if glycolysis takes place in all cells, that's going to be a huge thing if you have a deficiency in pyruvate kinase. Thankfully, it is very rare, and severe cases are not compatible with life, obviously. Okay. What I want you to focus on as an exercise, though, is the following. You see, it says there symptoms. Hemolytic anemia. swelling and immature rupture of red blood cells. Why would you think if a person has a disorder of glycolysis, why do you think they would get bursting of their red blood cells? Does glycolysis happen in red blood cells? Yes, glycolysis happens in all cells that have a cytoplasm. The next step is the Krebs cycle, right? After pyruvate. Maybe you know that from last year. Where does the Krebs cycle take place? Anybody knows? Mitochondria. Do red blood cells have mitochondria? No, right? So what are red blood cells dependent on for ATP production? Glycolysis. So if red blood cells cannot do glycolysis, it is detrimental for them. They eventually have no major source of ATP, and this generates a cascade of events that lead to the bursting of red blood cells. So whenever you see like hemolytic anemia, which is the bursting of red blood cells, one of the things you can have in back of your head, if you're suspecting a genetic cause, is a disorder of glycolysis. Although, mind you, they're quite rare. Okay, don't worry about memorizing treatments or how rare or frequent the diseases are. I just want you to know that, do the following thinking process. Okay, if pyruvate kinase is deficient, then we have a defect in glycolysis. This is going to be very, very important, especially in red blood cells that depend on glycolysis. So you get things like bursting of red blood cells. Okay. And then how is glycolysis regulated? Well, it shouldn't be a surprise that the steps that are regulated are the steps 1, 3, and 10. I think the thing that I will say most from now until the end of the class is steps 1, 3, and 10. Okay, so these 3 steps, they have a single arrow. Remember, they don't have an equilibrium arrow, and therefore are the regulatory steps, because they're the ones that are going to differ between glycolysis and gluconeogenesis. It kind of makes sense that they would be the regulated ones. So how are they regulated? Okay, hexokinase. Remember, hexokinase converts glucose to glucose 6-phosphate. Feedback inhibition. What does feedback inhibition mean? Who knows? When somebody says this enzyme is inhibited by feedback inhibition, does anybody know what that means? Yes?
It's inhibited by the product.
Exactly. It means that accumulation of its products inhibit the formation of more products. So G6P, which is the product of this enzyme, when it accumulates in high concentrations, it inhibits the formation of itself. So this is the most straightforward type of inhibition you can get in biochemistry in cells. PFK is the major regulation point, so I'm going to have slides dedicated to just PFK, so hold on to that thought. And pyruvate kinase is inhibited by high ATP. Isn't that also feedback inhibition? Isn't ATP a product of glycolysis? If you go back to the reaction of pyruvate kinase, you see that ATP is a product of this enzyme too. So that's also feedback inhibition. Pyruvate is also inhibitory. Yes, because it's a product. So again, feedback inhibition. And there is activation by high fructose 1,6-bisphosphate. If you think about it, fructose 1,6-bisphosphate is an intermediate well before pyruvate. So it's like being proactive. When an intermediate accumulates, it means the next steps will be required in high levels. So fructose 1,6-bisphosphate is activating, while its products ATP and pyruvate are inhibitory. Okay, so essentially feedback inhibition and stimulation by accumulation of intermediate fructose 1,6-bisphosphate. So for steps 1, 3, and 10, the name of the enzyme is something you need to know. The reactant and the product is something you need to know, and how these steps are regulated. Okay. So more about PFK. Now, before I explain how PFK is regulated, I want to explain using this table an important concept that applies to essentially cells that you may not be aware of. So this table here shows you the three guys there, ATP, ADP, and AMP. I'm sure do you guys know? Adenosine triphosphate, diphosphate, monophosphate. The only way they differ between them is a phosphate. So in a cell at rest, usually we have 5 millimolar ATP, 1 millimolar ADP, and 0.1 millimolar AMP. These are usually the ratios between these guys. So when we use a lot ATP, because of whatever reason you can imagine, you're exercising, you're utilizing ATP because you're moving around a lot, you have metabolic pathways that are requiring a lot of ATP essentially. Usually, this will get the ATP concentration down to 4.5. Usually, it's 0.5 millimolar of ATP that we use. That's only a 10% change in ATP, right? If you go from 5 to 4.5, that's a change of 10%. Now, ADP is 1 millimolar. It usually remains the same. Usually what happens is ATP becomes ADP and then AMP. So usually what fluctuates is the concentration of AMP and ATP. So AMP is usually 0.6. If the 0.5 of ATP eventually becomes AMP, AMP will go from 0.1 to 0.6. That is a 600% change. So what I'm trying to say with this table is that the signal that seems to be the most sensitive signal for the cell's energy status is not the ATP concentration, but it's rather the ATP to AMP ratio. See what I'm saying? Because the change in AMP, a small change in AMP is relatively large, right? So when you have 100 people in the class and 2 are missing, are you really going to notice? No. But when there are 10 people in the class and 2 are missing, are you going to notice? Probably yes. It's a relatively bigger change. Same goes here. Because the change in AMP is relatively bigger, it seems that the ATP to AMP ratio is the most sensitive signal for glycolysis. The cell doesn't just sense, oh, how much ATP do I have? It actually senses how much ATP I have, how much AMP I have, and how did the concentrations change. Okay, so PFK is inhibited by high ATP, is what people usually say. But in reality, it's the ATP to AMP ratio. And it's also inhibited by high citrate. We haven't seen citrate before, but perhaps some of you know that the Krebs cycle is called also the citric acid cycle. That's because citrate is in the Krebs cycle. So I put it here just because it is part of this, but to fully understand that, I will explain it again when we do the Krebs cycle. Okay, so I just want to put here that you see it says here, in muscles, the regulation of glycolytic enzymes is based on the ATP to AMP ratio, and this is the explanation. So here are some diagrams to explain that are coming. Another, yes? Yeah, usually in the cell, when these are the concentrations that you see. So usually the ATP concentration is much higher than the ADP than the AMP. Usually the ADP stays the same. We convert ATP to ADP to AMP, AMP back to ADP. So it seems that the ADP is rather stable. And the major changes happen at the 2 fluctuating ends. But because AMP concentration is much less, smaller changes seem bigger. I don't know if that answers your question. It's the example with the number of people in the class that I said before. A smaller change, it seems bigger if the number of molecules is smaller. Okay, another thing about PFK, remember PFK can convert fructose 6-phosphate to fructose 1,6-bisphosphate. That's the reaction it catalyzes. However, when concentrations of fructose 6-phosphate are high, PFK can produce what we call a side product. This side product is fructose 2,6-bisphosphate. In other words, when F6P is high, PFK can add a phosphate to carbon 1, but also to carbon 2. So you can get the actual product that you need, which is fructose 1,6-bisphosphate, but you get this side product, which is fructose 2,6-bisphosphate. And what happens is this side product, this fructose 2,6-bisphosphate, activates the PFK further. In my mind, I always remember it as fructose 2,6-bisphosphate telling the PFK, you've made me, I'm not the right product. So get your act together and make more of the right thing. That's kind of what it means. So the fructose 2,6-bisphosphate is a side product of PFK produced only when fructose 6-phosphate is high. In other words, when glucose is high, when glycolysis is high. And what does this fructose 2,6-bisphosphate do? It enhances PFK further, so it enhances glycolysis further. So if a cell has high fructose 2,6-bisphosphate, it means glucose is high, glycolysis is high. Okay, so this is what's called feed-forward stimulation. A product increases the production of more products. Is that okay? So you see PFK is regulated by ATP to AMP and fructose 2,6-bisphosphate levels. Okay, so you guys are masters of enzyme kinetics, aren't you, by now? Yes, you are, I hope. So if you look at this graph, it shows you on the y-axis is the PFK activity. It's the activity of PFK. And on the x-axis, you see the fructose 6-phosphate concentration. That's the substrate concentration. And you see the curve, which is blue, which is the curve without fructose 2,6-bisphosphate. And then you see in red the curve with fructose 2,6-bisphosphate. And I hope from your knowledge of enzyme kinetics, you can see that in the presence of fructose 2,6-bisphosphate, you achieve maximum activity at lower concentrations of the substrate. And the Km is also much smaller, which means the effect of fructose 2,6-bisphosphate is stimulatory. Is that okay? I just wanted to prove it to you with things that you already know. So here's what happens in resting muscles. In resting muscles, there's very, very little demand for ATP. So glycolysis is kept at a very low level. I just want to clarify that when we say a pathway is inhibited, it doesn't mean it doesn't work at all. It just means the pathway happens at a very low rate. Okay, so this is what happens in resting muscles. You see there is inhibition of PFK. Why? Because you're not using up ATP. ATP concentration is higher than AMP. You see here, they have the font size difference, indicating that ATP is higher than AMP. So, because the ATP to AMP ratio favors ATP, this is inhibitory. This inhibits pyruvate kinase as well. And then we have glucose 6-phosphate inhibiting hexokinase. So when you're not working out, glycolysis is kept at a low. Now, when you start working out, then inhibition is released. And so you get activation. So in biochemistry, that's oftentimes the case. Pathways can be activated because you've released the inhibition. So you basically now switch the ATP to AMP ratio. You're working out now. So ATP is being converted to AMP. So now the ATP to AMP ratio is decreasing. AMP concentrations are rising and ATP concentrations are dropping. This will stimulate PFK. It will release the inhibition from pyruvate kinase. You'll be using the glucose 6-phosphate, so the inhibition to hexokinase will also be released. Does that make sense? Any questions? So summary so far, glycolysis, by definition, the conversion of glucose to pyruvate, and more specifically, the conversion of 1 molecule of glucose to 2 molecules of pyruvate. Okay? And there is a net production of, in addition to the 2 pyruvates, 2 ATPs and 2 NADH molecules per molecule of glucose. At the end, I'm going to be doing some ATP accounting for you. I'm sure you've learned before that every molecule of glucose gives you, and everybody learned perhaps a different number depending on the book they were studying in high school. So 32, 34 ATP, or 30 or 32 ATP. So I'm going to get there, and I'm going to explain why there's an OR. And to understand why there's an OR in the total number of ATPs, I'm just keeping track from here. Okay, out of the 3 steps of glycolysis, 3 are the non-reversible ones, 1, 3, and 10, and these are the ones you need to remember. Okay, PFK is the major regulator for these 3 steps. I'm just putting it here so we're all on the same page. Enzyme name, substrate and products, and how they are regulated. Okay, any questions? So usually this is where I split the 2 lectures, because then we're going to go into gluconeogenesis. And since they split the lectures for us today, I will continue with this tomorrow. So I think if you go tonight and spend maybe like 30 minutes just going over glycolysis, tomorrow will make more sense because I'm going to go the other direction. Okay. Any questions? So we'll finish this off tomorrow.